right. You're first, definitely. Yeah. Yeah, that's really strange. One thing I would do is to re-download the processor 0004 and all those files, just in case somehow the processor um, uh, is corrupted, or some content of especially the ROM file, because if the ROM is corrupted, if the microcode is corrupted, then obviously the processor would do something that's not intended. It sounds like that, and because the file was too big, I think Google Sheets just kind of gave up, and that's why it didn't display anything. Yeah, yeah, sure, absolutely. All right, we got people signing in to Discord, so that's good. Um, why the post about River Spider? Well, it's just a tool, because from now on, we are gonna be writing actual code, and to debug your code, having the ability to trace your code is going to be quite useful. And River Spider is an automation tool. You can do everything without River Spider, but having it definitely helps. So it's not a required tool. You can do without. It's just that it's convenient to have it too. Yeah. um, Originally, if you read the README file, originally I was intending to basically automate not just the assembler, but to automate a whole bunch of stuff using a client that's running from a CLI. So and unfortunately, that plan did not pan out when District IT decided to add second factor authentication. So the script wouldn't work anymore, because somebody needs to be there to click, yes, send me an authentication token. So that's why it's called River Spider. I just never changed the name. Once it's River Spider. River means the river part comes from American River College, um, and then the spider comes from the being able to traverse the web. So that's, yeah, I know it's really kind of lame, but that's how I came up with that name. So yeah, I actually lost a few other tools, because I already have some tools, for the department, where I need to get onto certain web resources autonomously. So the script would just run every morning. I synchronize enrollment in certain classes. Synchronize all the accounts that I create on the Power server and so on. And then when the district implemented second factor authentication, that script did not work either. So I had to change a lot of things, because the district decided that um, we need to protect our grades and records and whatnot, which I think is good. But at the same time, a lot of the tools that I made stopped working. So all right, one of these days I will probably find a way to get around it, but that will have to wait. All right, so we're gonna get started with today's class. I already did a recording, so if you go back to the text channel, I have a link to a recorded portion that talks about the lab on last Thursday. So that part is kind of important, okay? Because there are some questions, where Batak, you never mentioned what the C flag is doing, and how does it relate to a compare instruction. So that part is intended for people, to encourage people to look into the processor and find out for yourself. So in the pre-recorded portion for the lab on last Thursday, There was some I wouldn't say instructions, but I demonstrated how you can do that. Basically, the entire processor is quote unquote open sourced, which means you can see everything. And it's about how you track things down. Okay, you start with CMPAB, you get to the opcode, so you might want to jot down these notes once the recording is done, so you can just kind of write down the time right now. So anyway, so you basically start with the mnemonic, which is CMPAB. You get to the opcode. Now you can get to the opcode either by hand assembling, which probably is what I would do, but you can also use the assembler to just look at the opcode, of CMPAB. And then once you have that, you can hard code that with a 0 on the right hand side into the microcode pointer, and then the ROM will then go to that location, and then you can actually track down all the multiplexers, demultiplexers, especially all the stuff inside the ALU, because the ALU is what is actually doing all the math stuff. So that was in the recording. So even though I'm being very terse right now, I actually demonstrated using and capture all the video in the recorded portion that I posted in the text channel. So there you go. So what we're going to do today is to get into how to structure a program. Okay, how do we implement conditional statements, that sort of stuff. So we are going to get into that in today's lecture. But before we go into that, I would like to demonstrate the conditional branch instructions, because it's not easy to understand how it is done, even though it's easier to understand what they do. So there's a difference between what they do versus how it is done. So this is the opcode table. You guys have access to this as well. So I'll just pick one of these. Okay, it doesn't matter which one. Since we talked about JCI, might as well just kind of stick with JCI for the time being. So JCI is about the same as a JMPI. JMPI, I think I explained that one already, because I remember that we talked about an infinite loop, and we demonstrated that one already. So JCI is about the same. You can see how JMPI is not conditional, but then when you look at JCI, let me bump up the zoom. Alright, so you can see how JCI is conditional because it uses a ternary expression, which means whether it gets whatever the program counter is pointing to in RAM, or whether it's just auto increment excuse me, or whether it's just auto incrementing, depends on the C flag. Okay, so we have to kind of look at the C flag. So the question now is not just how this is done, but the question is how it is done. Oh, I take it back. The question is not just what it is doing, but how it is done. So the first thing we do is we take a look at the opcode. This one is just 4-4 because 0100 is 4 in hexadecimal, so it just repeats itself. So this is a 4-4. Alright, so I'm going to switch back to Logisim, which I got running already right here. And I'm going to reset the whole thing. So go to simulate and then reset simulation. And I'm not even going to bother to actually write any code here. I'm just going to put in I'm just going to put in the microcode pointer here, I'm just going to put in 440. So this is what I mean by, once you get to the opcode, which normally needs to be fetched from RAM, put it into the instruction register, and then when right after the decode cycle, then it gets loaded into the microcode pointer with an extra 0 on the right hand side. And that's because of the way this splitter works. Is bit 0 to bit 3, they're all basically just zeros in, so everything is left shifted 4 bits. So this is a quick and easy way to kind of go straight to the ROM location corresponding to a certain opcode. So this way we can just go ahead and figure out, okay, how is this done? Okay. All right. So this part is also important. I posted a quote unquote thread in the questions channel of how do we study this stuff? Okay, how do we get ready for exam 2, which is going to come up soon? So I'm going to kind of try to explain the process. Even though I designed the processor, I don't remember all the details. Okay, I'm really terrible at remembering details. So every time I need to figure out something, even though I actually invented this, I developed this, I still have to go through all the process. So I'm going to describe the process. All right, so combine. So the first thing is, we have to go back to the opcode table first, because we want to understand, what are we looking for, right? So at this point, we know the program counter is one of is the centerpiece, right? Because you can see how PC is being changed, and we are also using PC itself to determine, the new value of the program counter. And on top of that, the C flag is also used in this case. So we're going to track down PC first, because PC is very easy to track down. So that's what we're going to do next, is to track down the program counter, which is right here. So I'm going to use not the poking tool, but I'm going to use the pointer tool to look into the program counter. So we know the program counter is about to be updated. One way or another, it is going to be updated. So this is the other thing that I want to emphasize. I already described this part of the process, or this step of the process, in the questions channel, is to look into dependency. In other words, what depends on what depends on what depends on what. So if you understand and basically have a mental picture of the dependency of all the different components in the processor, you will start to ask these questions naturally, right? Because you're looking at the program counter. You know it is enabled because PCEN is a light green. So the natural question to ask is, okay, what value is it going to be updated to? So then you have to track down the D port. So track down the D port. Let me just zoom in, maybe just one level. There we go. All right, so you need to track down what is going into the D port, and the D port is always coming from a multiplexer for the program counter. And since this is a multiplexer, what is then becoming important is which input of the multiplexer is going to be connected to the output. So that's the chain of reasoning, right? Because we have a dependency. We want to find out. We know the output of this multiplexer is important. So the natural question is, okay, what are the inputs into this device, and how is the output connected? So the two inputs here is part of it, but the most important part is the selector. So the selector is the one that is under the gray dot. That is determining which one of the inputs connects to the output in the case of a multiplexer. Now this multiplexer is relatively simple because it doesn't have its own enable pin. So it's always enabled. So that means we don't have to worry about, are we enabling this multiplexer? Well, it doesn't have a switch. It's always on. So now we look into the selector itself, okay, which is PCMux. Now PCMux itself does not come from the ROM directly. That is important, okay, because we don't want to make an assumption. We want to know what is PCMux, okay, what is this node connected to. So you basically highlight this, okay, there we go. So we can see PCMux also connects to here, but then when you look into the output of the ROM, none of these wires is highlighted. It's not thick. None of these wires are thick either. That means PCMux itself as a tunnel is not connected straight from the output of ROM, which then asks the question, okay, so this is what should be going on in your mind is, then what determines the value of PCMux? So now you look into this. I know many of you have a larger screen and it's easier for you to search and find that stuff. But then you can see, oh, PCMux is right here. Look at all of these wires, okay? They belong to the same node, and that's why they're all highlighted at the same time. So this is PCMux, and PCMux turns out to be the output of this multiplexer here. So once again, right, chain of reasoning, okay, look at the dependency. Once we track down, we are looking at the output of this thing here, then you need to look into what are the inputs into that device, because the output depends on the input. And that's why you need to ask that question is, okay, so now we know this output is important. How do we determine, what is going to be the output of this multiplexer? So this is a multiplexer again, and with a multiplexer, you don't look at the input pins first. You look at the selector first. So now we look at this selector, and this selector is PC Mux Mux because it is a multiplexer to a multiplexer. That's why it's called a PC Mux Mux. So in this case, it is 0, 0, 0, and this one does come out of the ROM because we can see how this wire is thick and it connects to a tunnel called PC Mux Mux, just like the one that we show up here. All right, so now we can see, we are connecting input 0 of this multiplexer to the output of the same multiplexer. So now we can just kind of focus on input 0 because the other ones are not important, okay? Because what connects to input 1 to input 7, we don't really need to know. Now it's useful to know that, okay? But right now our task is to find out how JCI gets the job done. So we track this down. It is coming from a splitter. The splitter, goes to an output pin here. The output pin is really just a probe. In other words, it makes it easier for us to see the content of a register in bits. So it's a convenience feature. But what is more important is it's coming from, so if you just click on the node itself, it highlights everything. So this comes out of the flags register. It's also coming out of the ALU itself. So the question is, I know this is bit 0 corresponding to the flags register because it is because this is actually just the bit 0 of this flags here. So we are looking at bit 0 of the flags register. But the question is, how does it get changed? So that part is explained in the pre-recorded asynchronous part of the lecture today, that explains the lab on last Thursday. So I really encourage everybody to kind of write a note here, watch the video about the lab on last Thursday, okay? Because this is the part that I don't want to repeat here, but you kind of have to watch that video. All right, so now we just know that, okay, so how is it conditional, right? Because this flag here, so sometimes flags register may have bit 0 being a 1, and sometimes it will have bit 0 being a 0. So how does that do all the magical thing? Because when we look into the opcode table, this is conditional, okay? If the C flag is a 1, we want whatever the program counter is pointing to in RAM. If the carry is, if bit 0 is a 0, then we just want to increment the program counter. So how does it get the job done? So to answer that question, there are two ways to do it. You can do it empirically, you can also do it analytically. So to do it empirically, basically it means you basically force a particular value into the flags register, make bit 0 a 0 or make bit 0 a 1, and then you observe how PC Mux changes and how that in return switches the multiplexers in one way or another. So that's the empirical way of doing things, and most people find that method to be more to be easier, to be more intuitive, because you can just kind of follow the wires. The other way is to do it analytically. Now to do it analytically, you now have to say whatever bit 0 is, okay, from the flags register is ultimately connected to PC Mux. So now we just have to track down PC Mux and see what it does, okay? PC Mux is a 1 if the carry flag is a 1. PC Mux is a 0 if the carry flag is a 0, given that we are now in the microcode slice of JCI. So now we get back here, we look at this PC Mux here. So all the PC Muxes are already highlighted. So that means, so this wire right here is telling you one thing, okay? It's really important. If the carry flag is a 0, PC Mux is going to be a 0, which means it's going to select input 0 to update the program counter itself. So in that case, okay, you track this down and go like, oh, so it's really just coming out of the adder. So it's taking the existing value of the program counter, and then it will add this value. We'll deal with that value in just a little bit, and then it will use that to update itself. Now, this particular value, which is carry in, which is what is equivalent to our K0 when we talked about binary addition, is coming out of a gate. Okay, so this is not a constant of 0, it's coming out of an OR gate. So that now we have to take a look at PC Inc. and also ADDR mux and say, okay, is at least one of these two a 1? Now, obviously, visually, we can tell at least one of these is a 1 already, which is address mux. Okay. So that's how, this is why the program counter just increments itself if and only if the carry flag is a 0 when we execute the JCI instruction. So I'm just going to pause because that's a lot of stuff that I just said, and I want to see if you guys have any questions. I just turned off the mic when I was sipping my coffee. Alright, so here comes a question. Can you do the empirical way so we can see the wires? Well, I am doing the empirical way right now because, the carry flag is indeed a 0, and that's how we can tell that the program counter is going to increment. So if you poke this wire, it is going to be 0, 1 because right now it is, the carry flag is a 0. That's why we see a dark green with PCMux. If you were to do it using the analytical way, you probably have to write it down because you need to track on a piece of paper what if the carry flag is 0 and what if the carry flag is 1. So right now we are playing out the scenario when the carry flag is a 0. So we can see that the program counter is just going to change to, 0, 1 when we have a rising edge at the clock. Oh yeah, but I want to pause here because this is basically the end of the first scenario, which is when the carry flag is a 0. So when if the carry flag is a 0, then the program counter will simply increment itself when we execute a JCI instruction, which basically skips over the immediate value. All right. All right, I'm not seeing any additional questions in the text channel. So we're going to move on. What if the carry flag is a 1? How do we do that using the empirical method? So that turns out to be not too hard because you just have to figure out, okay, how do we make the flags register having a bit 0 of 1? Well, I think the bit pattern corresponding to 0, 1 is going to have bit 0 being a 1. Yes, I just said that, bit 0 being a 1, because that's exactly what we're trying to do here. So you can see how, once we get past the splitter, bit 0 is now a 1, which is then connected to PCMux. So now the question is, how is that going to impact the way that we update the program counter? So the first thing we notice is the PCMux connecting to this multiplexer is now a 1. Not really surprising because PCMux is the carry flag or bit 0 of the flags register right now, which I not hard code, but I poke a 1 into it. Alright, so what's going to happen next? Well, this multiplexer is going to say, I'm going to pick input 1 to connect to my output. So now we have to track down the input 1. That in return is coming from this multiplexer here. So now we have to find out how we compute the select value of this multiplexer. So this particular select value here is coming out of an AND gate. This AND gate has a non-negated input from PCMux itself, and it has a negated input coming from RO0EN. Register output 0 enable. So you can see how that is a dark green, which is a 0. Once you negate a 0, it becomes a 1. So then we end up with 1, 1 to the conjunction, and then the output of the conjunction is going to be a 1, which means from the perspective of this multiplexer, we're looking in input 1. So input 1 of this multiplexer connects to, guess what? The data port of RAM. So here's the data port of RAM. So So now we look at the dependency thing again, right? So now that we know we are ultimately connecting the D port of RAM to the program counter's D port. Now the two D ports, they're both abbreviations of data, but the purposes are quite different in this case because RAM is actually outputting through the D port, and then the program counter is inputting through its own D port. And this is a little bit weird because RAM has a bidirectional D port. It can both be output when we are reading from RAM, or it can be an input when we are writing to RAM. So that means what is the next question that we need to ask? Because I want to make sure that you guys understand the process of how to formulate these questions into a chain. They're not really a chain, it's more like a tree because one thing splits up into multiple things. But nonetheless, okay, there is a list of questions that you should generate for yourself when you know something. This is, in this case, this is the output. What are the inputs, right? What are the inputs of RAM? Uh-huh. Yep. Okay. That would be the first thing I check, is to make sure the LD is a 1, and indeed it is a 1, which means this makes sense because RAM is in read mode. It is outputting through the D port. What would be the next question? Now that we know RAM is being read, what would be the next question to ask? We already know where it's outputting to, okay? Because the reason why we tracked all the way to here is we tracked the input of the program counter, and that's through the two multiplexers and also through the calculation of the selectors of the multiplexers. That's how we ended up here. What address? Okay, that's a very good question to ask. Well, okay, there's a trivial question to ask, is it selected, right? Because if the RAM is not selected, it's not going to do a single thing. So we just check that and go like, okay, yes, it is selected. So the next meaningful question is, what location are we addressing? Who is determining what location we are reading? So you look at this and go like, oh, it's reading location 00, and this is how we usually start a program. No, that is not the answer, okay? That is not the answer because it doesn't tell us who is responsible to specify this location. We need to know who is responsible to specify this location. So now we have to track it down. Okay, it's just like one of those puzzles that you do when you were a kid through a maze, right? So now you have to find a path from the cheese to the mouse, something like that. So now we track down the A port, and the A port is coming out of this multiplexer. And as a multiplexer, once again, the most important input to a multiplexer is the selector. So in this case, the selector is ADDR-MUX, which comes right out of ROM, so we don't have to figure out how it's computed. It is just simply specified by a location of ROM. And it's a 1, so that means we are looking into input 1 of the multiplexer, and that took us all the way back to the program counter. So we have just finished one loop. The program counter drives the address port of RAM. RAM is in read mode. The output of RAM, which is through the D port, goes all the way around through two multiplexers into the input of the program counter. This is why it is documented over here as asterisk PC, because PC is specifying the address in RAM where I'll be reading, and then I'll take that location, I'll take the content at that location and use that value to update the program counter. So this completes a walkthrough of how an instruction works. And I have to tell you, all of these conditional branch instructions, they are the more complicated instructions. The rest are fairly simple, because they are just going like they're just a lot simpler because there's no critical conditional part to that. So the analysis doesn't have to say, okay, what if this is a 0 and what if it is a 1? For the rest of it, it's just like, okay, it's just one path. There's one way to analyze the instruction. The conditional branches are slightly more complicated because you have two routes. There are two alternatives, and it's good to analyze both of those both of those routes. Alrighty. And you can see JLI, JOI, JSI, JCI, and JZI, they're kind of the same thing. So if you know how one works, the other ones are pretty much the same. The only difference is which bit do they look at out of the flags register. Okay, it's bit 0 all the way out to bit 4. Choose one. And these 5 instructions would choose a different bit out of the flags register. All right, so Chris wrote, so when we write a loop, it uses of the one of these 5. Yes. So JXI, the X is really just a placeholder for the flag that we want to pay attention to. And there are only 5 flags. Okay, we explained the C flag, which is basically both the K and also the T of the binary addition and subtraction module that we talk about. And yes, I know someone is going to say, but why do we combine both into one? Why don't we separate it into a B and then a C flag? Now, this is just convention. Okay, I could have used a B flag for subtraction and a different flag, C flag, for addition, but that's just not how things are usually configured in a commercial processor. So I decided, maybe for once I'll just kind of implement things as the usual way as the other processors. And then JSI is the sign flag, which is basically just the most significant bit of the result of an operation. So after an add, it'll be the same as S7, the bit 7 of the sum. After a subtraction, it will be the same as D7, which is bit 7 of the difference. JOI is really just the overflow flag. And the overflow flag is computed, we already know how that is computed for subtractions, and then for addition it's computed slightly differently. But what it means is, when the overflow flag is a 1, it means, we have run out of the range of values for addition or subtraction, depending on what the prior instruction is, when it comes to signed representation. So we have a value after an addition or subtraction that cannot be represented using an 8-bit signed integer. And then JLI is just saying, okay, if the L flag is a 1, we use whatever the program counter is pointing to in RAM to update the program counter itself. Otherwise, we just increment the program counter itself. And this is the same L flag that you have already used in exam 1. I'm still grading exam 1, so that's why this stuff is really kind of still fresh in my mind. Yes, that is coming along, but it's coming along really slowly, slower than I expected. Partially because I was trying to read through every single line of reasoning, and that takes time. That just takes time, because sometimes some of those explanations were not very clear, and I would be trying to figure out, okay, but what do you mean by this? Okay, let me read this again. Oh, okay, I think I get what is being written there. So it's a slow process. It's a very slow process, unfortunately. I wish I could do it faster. Anyway, are there any questions here? Are there any questions regarding the conditional branch instructions? They're really, really important when it comes to the control structure of a program, which are basically your conditional statements, your loops, and so on. All right, so I don't see any questions. All right, well, without any additional questions, I am going back to where's my stuff here? Nope, this is from a wrong class, and that's from a wrong class too. Lotto, yes, I was using Lotto to explain stuff. And oh, okay, that's just bro taking from last time. All right, so let's go ahead and take roll. I got it ready, so might as well do it. And let's see, where are we now? Oh, it's right here. So from your perspective, it is. Oh, let me move it first because otherwise it's just gonna be a little bit confusing. So I'll move it all the way up here and then make it visible. So it should be visible now. but you won't know the word until I show it, because I cannot remember either. I just said it like this afternoon at about 4 o'clock, and I cannot remember what word I have chosen to use. Okay, so what is it? It's JLI. Alright, so JLI, paste it into the text channel. There we go. And then I have to specify the time. It is already published. I'm not sure what happens if I don't specify a due date or due time. So I'm just gonna give you guys, I'll give you plenty of time. 6:30. That should be plenty. Alright, there we go. So if you refresh, you should be able to get into the road taking activity, and then the word is JLI. It's not even the word, it is called a mnemonic. Jump if and only if less than immediate. Alright, so as you guys are doing that, I'm going to go back to the modules. Oh, I got one more thing that I need to demonstrate, because that's going to be it's going to be interesting. I think it's important to demonstrate it. So we'll go ahead and wait a little bit as people try to get the road taking thing done. Alrighty. Oh, I still have this code here. That's the from the test program. Alright. Alright, so I'm going to assume people are getting the road taking thing taken care of right now. So we're going to look at this program a little bit. The no op is needed if you want to trace the code. The first instruction has to be a no op. That is probably a bug in Logisim. I didn't have time and never got time to actually figure out why that is the case, since there's a very easy way to kind of get around the problem. So you have to start with a no op if you want to use the trace analyzer. LDI A5 is just saying, okay, let's put the value of 5 into register A, because we actually traced through LDI in one of the classes, so we should know what LDI A5 does. And then here we have AND AA. Okay, so the question is, what is this instruction doing here? What is AND AA doing? So to answer that question, you can ask me, I'll give you a response, but I may not actually be telling you exactly why it is here, because I want you to find out for yourself. Today's lab actually has that question. Okay, it actually uses AND AA in a certain way, and it explains it. So to fully explain, to fully understand, in this context, what AND AA is doing, I would encourage you to do exactly what I just did with the JCI instruction. Okay, just put it in to the simulator, right? Just go to the simulator and just kind of hard code in the opcode, but shift it 4 times into the microcode pointer, so that we end up at the location corresponding to AND AA. And then what you want to do is to kind of go through, all of these things. Go through, the register bank, go through the ALU, and find out exactly what it does, but including all of the side effects. Okay, because in this case, when you execute AND AA, you will find that the flags register is going to be enabled. In other words, it's going to update the flags register. And you want to find out how it is going to be updated, which means you're going to have to go into the ALU to find out how the Z flag, which is this one here, how it is computed, and which bit position is corresponding to the Z flag, which is kind of spelled out right here. This is the Z flag, it is bit position number 1, and so on. Okay, so you want to repeat that process. You want to repeat the process where I dissected the JCI instruction and kind of showed you and explained how it gets the job done. And you want to do the same thing with the AND AA instruction. Just so that you are familiarized with the processor, what is where, what it does, and so on and so forth. So that's going to be an exercise, for you guys, not when you're doing the lab, but I would do it after the lab, like shortly after, when you still have all the when you still have the context. All right. So the next instruction is JZI, which is a very close instruction when it comes to how it gets the job done with JCI. The only difference is this one looks at the Z flag instead of the C flag. So you want to understand what the Z flag means. Okay, what does it mean when the Z flag is a 1? Okay, that's kind of the question. That particular question is already, you can find the answer to that question over here, which is which has to do with this part of the circuit. This is the Z flag. So now you have to ask yourself, what is this gate here? Okay, because Tech, you never talked about this gate. What is it? Well, to answer that question, you turn into the poke tool, not poke tool, you turn into the selection tool and you just click it. It tells you it's a NOR gate. Okay, it is a negated OR gate. And it has the inputs. There's a bunch of inputs here. What are those bits? Where are they coming from? It's coming out of a multiplexer. So in the case of an AND AA instruction, which input connects to the multiplexer. Those are the questions that you should be able to answer at this point of this class. So that's kind of what I would like you guys to do. I mean, in the questions, channel, I kind of lay out how to study, how to prepare yourself for exam 2, now that we are talking about the actual processor architecture. So you probably want to head over there and let me see if I can just kind of post a link to that thing. Right here. Only one of those 8 can be a 1 for the flag to be true. It's a NOR gate, right? So I think you need to remember to do the negation. Alright, so copy message link. I think that should work. And then go back to today's text channel. And then paste it here. Alright, so I just pasted the link. Not sure whether it's going to work or not, but that's a link to the quote-unquote question that I posted in the questions channel and then answered it myself. Yes, I'm proud of myself to be able to answer that question. But so basically, it kind of outlines how to study for this class. So this is so getting back to this gate here, this is a NOR gate, right? So that means it's a negated OR. Now a regular OR is going to be a 1 if at least one input is a 1. So in order for OR to be a 0, all of the inputs need to be zeros. But since this is a NOR gate, that means it is negating a regular OR gate. So if a regular OR gate can be a 0 only if all the inputs are 0, that means a NOR gate would be a 1, would output a 1, if and only if all inputs are zeros. In other words, Z flag confirms that the result of an operation is indeed a 0. That's the way it works. Alright, so getting back to the code. So switching back to the code here. So all this is doing, between these two instructions, is really just saying, okay, let's check whether A is 0 or not. That's basically what they're doing together. And if so, go to label L2. So this is label L2, and we can see once we get to label L2, there's nothing to do. We're done. Okay, we're gonna halt. So what does it mean what do we do when this is not branching to label L2? In other words, what if AND AA, what if register A has at least one bit being a 1, which means register A is not 0. If register A is not 0, we are going to get to the decrement A instruction. You can do the same thing, okay? After the lab, analyze, how decrement gets its job done. So you might say, oh, how hard can that be, right? Because we are just subtracting 1 from register A, and we already know how to do compare, which is a subtraction. How hard can this one be? Well, as it turns out, it's not as simple as we think. Okay, because it actually took me a little bit of time to figure out, how to decrement a constant from a register, because the subtractor needs 2 inputs, right? And the way I had the circuit laid out is both of those inputs need to come from registers. So there's no way to actually decrement because you will first have to load a value of 1 into one of the other registers in order to do a decrement, and that is super clumsy and unnecessarily clumsy. So it took me a little bit of time to go like, okay, how do I, kind of change things a little bit so that I can feed a constant of 1 into the ALU so I can increment and decrement. So once again, to that little mystery, you can solve that mystery by looking into the TTP architecture. Okay, so we have all the tools already. It's the whole thing is open sourced, which means you actually get to see every little part and how they connect in the processor. And by doing this type of analysis, you are basically studying. That's how we study for this class. It's not just just reading some text and try to memorize anything. Nope, it really has to do with it's an exploration process, and so that's a little bit different compared to your other classes, I suppose. All right, so now we get to, so after the decrement A, which decreases the value of A by 1, then we use the unconditional branch JMPI to L1, so that means we get back here, we check whether A is 0 or not. If it is 0, we get out. If it's not 0, we decrement A again, and then we go all the way back. So this is basically a while loop, to basically decrement A until it is 0. So if you want to look at this while loop here, this is one way to document the while loop. So I can put everything into one single line. So A gets 5 first, and then we say while A is non-zero, we stay in the loop. And in the loop, the only thing we do is to decrement A, and that's it. So this is the C equivalence of the code that is now written in assembly. Do we have any questions? I'm going to pause here a little bit and see if you guys have any questions. You guys are confirming way too fast because I was still drinking my coffee. Not something that I can do in an actual classroom. How does ZJI halt works? It's 2 instructions, right? We have JZI as 1 instruction. Once it gets to the label L2, it executes the halt instruction and then it stops working. So together, it means if and only if A is a 0, then we continue execution at label L2, which means we are done with the program and we halt. Now, obviously, the next natural question, if I were you, I would be asking that question in my head is, how does halt work? Okay, because we know what no op does. Okay, that's something that we talked about either on last Thursday or last Tuesday. I cannot remember which day. So no op is really a byproduct of the fetch cycle itself. Okay, which is at location 000 of the ROM. So no op is kind of a free instruction. It just so happens to be there as opcode 00. But how does Halt does its job, which is an important job, but it's a very weird job, is to basically stop the processor from going any further. It's like, okay, we are done here. Let's just not do anything after this point. So that's also a question that you can answer by analyzing the processor the way that I just did. Okay, you just hard code 010 into the microcode pointer, get to and then analyze the pathways within the processor. But I'll give you a clue this time. You only have to look into the microcode pointer, okay? Because everything else is going to be off. Okay, so you want to understand why is the halt instruction be able to basically stop the program from advancing any further. So once again, those are the things that you need to be able to figure out. The first time you do this, it's going to be slow because you're going to have a hard time finding the components. The more you do it, The quicker you can find the components, the quicker you can actually go through the multiplexers and demultiplexers. So you really kind of have to, I mean, there's no shortcut to do this. Okay, you really just need to spend the time to work on it. Alrighty. All right, so getting back to my original point, okay? So the original point of looking at this program is, attack, how do you confirm that this is a loop? And A starts with 5, and then it changes to 4, 3, 2, 1, and then when it gets to 0, we get to the halt instruction. That's what I claim the program is going to do. But how do we know this is actually what the program is going to do? So I'm going to show you the long way of doing this. So this is a technique that you can also use to test your program that you're going to be writing today. It is not necessary. So if you think your program is going to work and you say, I don't need to test it, just turn it in. Okay. And on the other hand, if you say, I'm not really quite sure, I want to test my program, this is one way to do it. And by the way, this program is included in River Spider. So for those of you who have it already installed or thinking about getting it installed, it is already included. But I'm going to show you a way that does not require River Spider to get this done. Alright, first thing first is to get to the RAM file. So here's the RAM file. And then we go to File. And then we get to Download. And I usually download as a CSV, even though you can download this as TSV. I just download as CSV because I reserved the extension TSV for something else. So so normally it wants to download using a rather long name with a space in it, which Logisim does not like. So I usually just change the name to something else. So in this case, I change it to test.csv, and I'm putting it into the temp folder. So there we go. It's already there. That's because I have done some other things before. So I'm going to replace it. No problem. So now we get to the processor, and the opcodes go into RAM. Okay, the microcode goes into ROM, but the opcodes go into RAM. So make sure that your processor is reset, because I just kind of played around a little bit with the microcode pointer, right? I remember that. So the microcode pointer is it's still kind of not at where it's supposed to be. So I'm just going to go to simulate and then reset simulation. There we go. And now I can safely load the program in, and we can start to execute the program. So you can do it this way, okay? But if you do it this way, then you're gonna have to single clock the whole thing, and you have to watch, how the register is getting changed. Let me just do that once, so you can see it. So I'm gonna load image, and this is, I'm not sure whether I can do it. Let me see if I can do this. Okay, it does work. So I specified the full path in the dialog box and just went to the right file, get the content in. So now you can do it in a few ways, okay? Because I want to keep an eye on register A, and register A is displayed here. But at the same time, I kind of want to look at the halt pin, which is down here, because that's an indication of whether the program is done or not. So the halt pin is right here. So you can do it this way, by reducing the clock speed a little bit, because otherwise the whole program is going to zip through, and you won't even be able to see how register A has its value changed. So this is one way to do it. I go to simulate. I change the tick frequency to something that's much more visible. Okay, if you change it to 4 hertz, it's going to be a little bit on the slow side. I'm going to use like 32 hertz. 32 hertz means 32 edges per second, which really translates to 16 rising edges. So this is going to be slow enough that we can actually see how register A changes. So for those of you who say, but I can't really track all of these things at the same time, well, I'm pretty sure you know how to do a screen recording, right? That's how you do it. Okay, download OBS, just screen record the whole thing, and then you have your own video to go through. Then you can kind of slow motion the whole thing and figure out at what time does A change and stuff like that. So we'll go to simulate and say tick enabled, and there we go. See, it's visible. And there we go. So once A is 0, we should be halting right now, and it is halting indeed. So now I can stop the simulation. There we go. You could click the text too. It's just going to take time. Now I'm going to show you the other way. Okay, since Chris is already asking, can we do it? Just do it manually. The answer is yes. Okay, you can do it manually. But just because you can do it manually doesn't mean that you should do it manually. So it's up to you guys. Okay, you get to decide whether you want to go through the trouble to run it in the CLI or to use River Spider or not, or to use the other program that I have linked up there earlier today or not. Okay, so that's entirely up to you. But what I'll do is I am going to show you a way to do this. It's kind of somewhere in between. It's not the full manual method by clicking in Logisim, and yet it does involve a little bit of CLI command line stuff that we actually introduced in week 1 or week 2. So that was a while ago. I started to talk about it because I knew at the time that we're gonna need it. Okay, so I wanted to give you guys plenty of time to kind of get comfortable with the CLI environment, and this is why. All right. So we still have the file in the temp folder. Let me just kind of change the layout so this way it's easier for you guys to see what I'm typing. There we go. Yep. Zoom. There we go. And let me move this to the right place. All right. So the full command line is to say Java, and hopefully Java is on the path environment variable, so this way you don't have to actually find the path to Java itself, because that's going to be a pain to type. That's jar, and then the path to my Logisim file, the processor 0004 file is in my home folder, and then documents, CISP310, and I'm going to use the one in the River Spider subfolder, and this is Logisim310.jar. So this will start Logisim, okay, but you don't want to press the return key yet, because if you did, it's going to run Logisim in a GUI mode, which is not what we want to do. So we want to also specify the circuit file, which is going to be in the same folder. Okay, so documents / CISP310 River Spider processor 0004.circ. Okay, so if you press the enter key right now, it's going to start Logisim in GUI mode, and it will also load the processor into the GUI, which is also not what we want to do. So what we want to do is to use a dash load here. It's called a switch in command line interface term. It's called a switch, but you can just call it an option. Okay, so this allows Logisim to automatically load the content of a RAM file into a RAM component. So now we just have to specify the name or the path to the RAM file, which I have just put into the temp folder. Yes, I know I'm in the temp folder and /temp is not necessary, but I'm just going to give it like full path names so that this way there's no assumption being made. All right, so there's a little bit more. You have to specify -tty. TTY itself stands for teletype, which is the original dumb terminal that people use to connect to mainframe computers. So teletype, as the name implies, is really a serially connected typewriter. And you heard me right. It is a typewriter. It actually prints on paper. So that's what a teletype is. Tele meaning remote, right? Type is typewriter. This is a remote typewriter. That's why it's hence the name teletype, TTY. All right, so you need to specify table. So I don't think it has any other mode to use TTY, the teletype mode, which is the command line mode. But you have to specify table. Now, if you were to press the enter key right now, after this gigantic long command line, it will run the program and it will give you the output. Well, the question is, can you interpret the output here? The answer is probably no, because I cannot do that. Okay. So the way we do this is we capture the output, we use the redirect symbol, the greater than symbol. Now, all of this stuff here, minus the dash load thing, we have talked about this already, because when I showed you guys how I grade your early assignments, like the carry look ahead adder, and some of the other circuitry, I gave you a test circuit, and this is how you run Logisim in order to capture the file, to compare to the key to see if your circuit works correctly or not. So that actually has been explained since I think week 1 or 2. Alright, so getting back to here. So I'm going to capture the output into test.tsv. Now this part is important, okay? Whether you download the RAM file as CSV or TSV doesn't really matter, because we are not really using a comma nor a tab as a separator. It's just using a space character as a separator in that case. So you can call it whatever you want. But the output of Logisim, if you run it this way, is really a tab separated value file. So TSV is the proper extension. So now we press the enter key, and the output is now captured in this file. Now, just to make sure that this file is captured here, we'll go ahead and do an nvim. This is just my text editor here, and take a quick look here. And that looks correct, okay? And if I were to look for the tab character, yeah, they're all here. So we are good. All right. So the question is, what do we do with this tab separated value file? Pretty sure we have talked about this already at least once, but I'm gonna do it one more time. So now we go to the trace raw data sheet. Okay, so there's a sheet called trace raw data. And then you go here, and then you go to file, and then you do an import, and then you specify the file that you want to upload, which is the TSV file that I have just captured, and that's going to be in temp.test.tsv. Press the enter key, it uploads the file. Then it becomes important. Okay, now you have to be careful how you choose these options. Harrison Ford only needs to choose carefully, choose wisely, not carefully, choose wisely for one single object in the movie. I'm not going to say which movie, because it's not important. But in this case, you have 3 things that you have to choose, and you have to choose wisely all 3 times. So we're going to have to choose replace current sheet for the first one. And then for separator type, do not let it detect automatically. You specify tab. And the most important one, which doesn't seem to make sense to most people, is you have to uncheck convert text to numbers, dates, and formulas. So these are the 3 options. Okay, so you might want to kind of jot down the time stamp, of around now, because you might need to get back to this, right? So you might want to jot down the date and also the time. So this way, if you need to learn if you need a reminder of how to use the trace analyzer, you know where to find that instruction. Alrighty. Oh, there's a whole bunch of text stuff going on in the text channel. In Windows, the Windows key plus G to screen record in Windows. Oh, okay, that's kind of handy. I just use OBS. I'm just a big fan of OBS. Alright, so we say import data, and it's going to update. Well, it's the same because I just ran the program again, but it's the same. So after a while, okay, you're going to go to analysis. So this one is different compared to the one that I use River Spider to upload. It's the same content, it's just not very dense. Okay, you can see a lot of empty rows here, and that's because it doesn't trigger the auto filtering mechanism if you were to use River Spider. So River Spider, invokes a filtering mechanism because it's going to a JavaScript, function, so it does automatically remove the lines that are not necessary, making the whole thing easier to read. That being said, it captures the same information. You can see how. Okay, let me explain the different columns. So column A is basically showing you what are the locations, okay, the location of the execution of opcodes. So this is saying, okay, we're getting to location 0 to execute the no op instruction. Now we move on to location 01 to execute the instruction of LDI A5, and that's why you see register A is changed to 5. That's the job of column D. Column D is going to reflect what register is updated, okay. It does show something in column B, which is location 03 has a content of C0. You can kind of ignore this one because it does go to RAM and read that location, but we are ignoring that read in this operation. It's kind of more of a side effect of auto incrementing the program counter as we get the 05 into register A. The next opcode is at location 03, and I believe that's the AND AA instruction. So we can see the AND AA instruction doesn't really change A because bitwise AND 05 with 05 doesn't change the value. But it does update register A with the same value, and that's why we see an entry here. But the important part here is it updates the flags register. Okay, so I already kind of quote unquote decode what bit is what, from the flags register. So instead of giving you 5 binary digits and let you figure out which one is which one, it's already decoded. I mean, that's kind of easy, right? So we now move on to location 4, which is the JZI instruction. So in this case, the JZI instruction did not branch because we continue execution at location 06. So for those of you who are asking, why is it skipping 05? What is at location 05? Well, you kind of need to have to go back to the JMPI instruction, the unconditional branch instruction, and find and remember from that discussion what is right after the opcode of a branch, using with an I as a suffix. So it's the same reason here, okay? So the branch did not happen. We just continue execution at location 06, which I think is the decrement instruction. And as a result or the side effect of the decrement instruction, you can see how register A is now updated to a 4. And then we get to location 07, which is the JMPI instruction. And that just jumps all the way back to location 03. And then we do the AND AA again. The 0 flag is a 0 because A is non-zero right now. We are not going to take the JZI instruction. Instead, we continue to decrement A again, and so on, blah, 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 blah. Okay? So without the capturing of the execution of the program, if I had a bug in the program, it would be really difficult to find out what happened. Okay? Because not only can I not easily track the symptoms of a particular bug, I also would not have a history of the execution of the program in order to find out how I got to the bug, how it happened in the first place. This gave me the entire history of how this program executed. Yeah, sort of. I mean, but this is a debugger. I mean, back in the old days, when I was an embedded system engineer, a trace analyzer hooked up to it's called a logic analyzer. So a logic analyzer is a physical device. It has one little clip per trace on the circuit board. Okay, you can kind of imagine all the crazy number of clips that it comes with. Okay, so we have one clip basically per bit in the circuit, and it would capture the signals going on to those wires, and then it will log all of those things. And once it understands this is a whatever processor architecture, then it will start to interpret what is happening, and then it will basically give you an output sort of like this, so that you can actually see the execution of a program when there are absolutely no debugger tools for that kind of environment. So I'm simply replicating some of the tools that I had, when I was doing that job back in the early 90s. Alright, so off topic, but we are at some point going to cover why programmers frown upon using GoTo. That is, well, that's not my job. That is not my job. That's the job of someone who's teaching a high level programming language. In assembly language, there's no way you can avoid the use of goto, which is basically JMPI. So JMPI is really just goto. Okay, specify a label and I will continue execution over there. There's no way to get around that problem in assembly language programming. But in a high-level programming language, such as C, C++, Java, JavaScript, Perl, Python, and so on, Ruby, and Visual Basic, C Sharp, and so on, doing that, basically encourages. I'm trying to choose the right word here. It encourages programmers who are looking for a shortcut to basically say, oh, I can just do this and then I can go home because this will fix the problem. So yeah, it will encourage that kind of behavior. Except they are not really fixing the problem; they're just patching a problem. So and the program gets more and more and more difficult to maintain as time goes on. I have had the opportunity to debug a subroutine written in C is part of a compiler that had 500 lines. Yes, it's a single subroutine with 500 lines in it. So right there, something is not right, right? And it had go-tos, okay? Now there are certain go-tos you would frown upon, but you will still go like, yeah, it's kind of understandable, okay? Which is a very exceptional condition, where okay, there's no way we can recover from this condition here. Let's just go to the return all the way at the end of the function, return the error code, and just call it a day, okay? So there are occasions where you can say, you will still kind of cringe on that go-to and go like, I suppose it's okay, okay? But this program is not like that. This subroutine had go-tos from a conditional statement inside a switch, inside a loop, going into the then branch of another loop, inside another switch, and so on and so forth. It basically crossed a bunch of nesting up and then crossed a whole bunch of nesting down. And, I just gave up. I couldn't figure out, what that code is trying to do, so I just had to re-implement the entire subroutine instead of fixing it because it was not fixable. Yeah, people with a military background can say it's basically foobar. Alrighty. So anyway, getting back to this trace here. So you just basically have to look at column D to find out, how register A is getting changed. So it went from 03 to 02, 02 to 01, 01 to 00. So once you get into 00, we still go to the unconditional branch instruction. And then we get back to 03, which is the AND AA instruction. Now this is important because right now we can see how the 0 flag becomes a 1 because 0 is represented by 00000000, which means we have all 8 bits being 0. So the NOR output is becoming a 1, and that's why we store a 1 into bit 1 of the flags register, and that is reflected here. So all of this discussion here, what you're seeing here, that relates all the way back to the earlier discussion of what is inside the ALU. So I'm hoping you guys are, not right now, but I think, eventually you need to make the connection between what we are looking at here, which is the trace of executing a program, with the architecture itself, which explains how it is done. This is what is done, and then the other one explains how it is done. So in this case, the conditional branch instruction at location 04, the JZI instruction does branch, and you can see how, the next instruction is no longer sequential to the one in at location 04. It is now at location 09. Now, for those of you who are looking at this and go like, but Tack, how do you remember which instruction is at which location? Well, this is a fairly simple program, and I can still remember that. What if you cannot? What if you look at location 04 and say, I have no idea what is at location 04? Well, that's why I put in the analysis tab right next to the assemble tab, because they kind of work well together. So when you go back to the assemble tab, you look into location 04. This is location 04 right here because column W is the address in hexadecimal. So now we can look into this, and it does correspond to the JZI instruction. So this is why the assemble tab is intentionally put right next to the analysis tab, because a lot of times I would have to kind of switch between these two tabs, like back and forth. Now the nice thing about Google Sheet is you can actually just copy the URL into a new window of your browser, and you now have two views into the same actual document. So that means if you have a screen that is large enough, you can actually have one screen to only look at the Assemble tab, and then another screen to only look at the Analysis tab. And that is nice because this way you don't have to lose track in one from one when you switch from one window to another window. It's easier to debug a program when you have visibility to the program itself versus what the program did when it executed. All right, so we have just kind of gone through a complete process of how do we look at the actual execution of a program. So this is how you do it, doing it kind of semi-automatically. It is still considered semi-automatically instead of not automatic at all, because we are still relying on this command line here to kind of put all the trace into a file, and then we have a tool on this side to look at the raw data and then turn it into something that's presentable, okay, something that does kind of show you what it does. So in that case, okay, what does the River Spider program offer that makes it kind of nice to have, right? So we'll go ahead and use the River Spider program to do exactly the same thing. This is how it is going to be done, assuming the program is already written. In other words, the TTP ASM is already available. So I go to Documents, CISP310, River Spider. This is where the script is located. The script itself is called submit.sh. sh is it stands for shell, shell, shell. So you just have to tell it where the source code is, which is the TTP ASM part of it. So this is the TTP ASM file, and then you press the enter key. That's all. So it will automatically send the file to the assembler, and when the assembler is done, it will get it back. It will automatically run Logisim and capture the output, the TSV file, and then we'll re-upload the TSV file back to the spreadsheet so that we end up with the analysis tab all finished up. And you go like, but Tech, this doesn't work. Your stuff doesn't work. Well, it actually works. It works really well because you can see how the output is now more compact. And that's because when I do it this way, it has to go through a filtering mechanism, and the filtering mechanism just kind of, as a handy feature, it gets rid of the empty rows. So this way, I can fit more trace events, onto the same page, which makes it easier for me to read the trace of a program. Alrighty, so I am going to kind of pause here. I'm not going to stop, but I'm just pausing to see if you guys have any questions. Alrighty, no questions. So I'm going to explain a term that some of you may need to ask, because it's not a very common term, and in the context of the lab, I can kind of understand why some people may need to ask that question. So sometimes I refer to a term called hijacking. So hijacking is basically saying, oh, certain opcodes are useless, so we can reuse that opcode for something that's meaningful. So let me point out one that is ripe for hijacking, but it's not the answer in the lab tonight. So we'll look at CPR. Okay, CPR is copy register. Okay, it is not a EMT term in here. It is copy register. So it literally really just takes the value of register Y and then copy that to register X. So both register X and Y are registers inside the register bank, which means X can be A, B, C, or D, and Y can also be A, B, C, or D. So when you look at this and go like, well, that seems pretty useful because occasionally we might want to copy register B to register A. So if you want to do that, then X is going to be 0, 0, and then Y is going to be 0, 1, which means in this case 5, 1, in hexadecimal is going to specify CPR AB, which copies the value of register B to register A. Okay, that's actually pretty useful. But then you also think about, but what if X and Y are the same? Right? I mean, what if you have CPR AA, or CPR BB, CPR CC, and CPR DD? That seems pretty useless. Okay? So now we say, but that takes up 4 opcodes, okay? Because CPR AA is 50, CPR BB is 55, CPR CC is 5A, and then finally CPR DD is 5F. So those 4 opcodes are basically useless because you're basically wasting processing cycle. We already have no op for that purpose. Okay, we don't need another no op. Basically eventually end up doing nothing that's useful. So hijacking means we are going to recycle that code to do something else. So that means instead of 0, 5, 0, doing CPRAA, which is utterly and completely useless, we can now say, I can invent another instruction to do something that's actually useful. Okay, now I have no idea what else I want to invent here, but I have that opcode now available. That is what I refer to when I use the term hijack in tonight's lab, is basically to look at an opcode that is useless in its original meaning, and I'm just going to reassign that opcode, which is the binary code in this case, to mean something else. Now, if you want to ask, what do you mean by doing something else? Let me show you graphically what that means. So to understand that part, I cannot do that without. Give me a second here because I need to restart Logisim. So I am just gonna do the lazy thing here and just get rid of all the other stuff, just having this part remaining, because all this does is to load up processor 0004 in a GUI mode, and this is what we see. Alright, so the reason why, so hijacking, right, back to hijacking. So we need to look into the ROM content, right click on it, and then say edit content. And obviously it's going to give me a gigantic window that won't fit on the screen, or at least not the portion that is being recorded. So I'm going to have to shrink it a little bit. Okay, there we go. So remember what I said, 5, 0 is utterly and completely useless. So what we do is we go to location not 5, 0, but 5, 0, 0. Remember that extra 0 is important because that's how we get to the location in ROM, based on the opcode of an instruction. So we can see this is 500, and it does actually just copy register A to register A, which means when you look at the meaning of that opcode, it is utterly and completely useless. So that means it's ripe for hijacking. So if I ever want to implement something like and immediate value of 1, now, I have no idea why I want to do that, but if I want, just ending a particular register with a constant of 1, I can use this location now. I can use this location to specify all the bit pattern in order for the processor to perform a logical bitwise AND with a constant of 1. In other words, I'm just singling out bit 1 to try to figure out whether it's a 0 or 1. So I could do that. Okay, so hijacking basically means go to a specific ROM location that is implementing something that is useless and change that to implement something that is actually more useful. So that's basically what when I use the term hijacking an opcode, that's basically what I meant in the lab. So are there any questions? We are right on time. Wow, look at that. It usually doesn't happen with me. With Damon Antos, always on time, down to the minute. So I'm looking at the text channel. Doesn't look like we got any traffic over there. Alrighty, so with no traffic over there, I am going to release the lab for tonight. So the lab tonight is, alright, so let me look for it. It's for finding the absolute value, so you're going to have to write some code to find the absolute value of a particular value in register A. So that's what you're going to do. This is lab ABS absolute value. And let's see. I think this one has a passcode. It's probably just ABS itself. Yep. Not much of a password, is it? There we go. And we have until 9:50 to work on this. Alright. Save and publish. So now you should be able to get into the lab and just type ABS as your passcode. And I'm going to go back and change a little bit more of the lab. You guys can go in and do it, but I am going to specify when to release the answers. So it's going to be 9:50 p.m. So as soon as it is due, it will show the correct answers, but only for the first few questions, because one of the questions require you to turn in your source code, and that one needs to be graded manually. Yep, I understand that one, Omer. My physician, my doctor, my family doctor said I'm borderline obese. He showed me a graph based on height and body weight. I was borderline obese, so I was right at the border. Pretty sure now I am actually obese. Well, using that chart. Obviously, my physician has never heard of the term yellow dwarf. And this is not a racial slur, okay? It is not a racial slur. This is an actual astronomy term to refer to suns that are small, okay? They're low in mass, by comparison. They live very long because they burn very, very, very slowly. And they're also physically small because they don't have the mass, or the fusion reaction to sustain, a shape or size that is big, and those are called yellow dwarfs. And there are red dwarfs as well, because those are even burning at a lower temperature, so they are actually red in color, and they're dwarf stars. They are small, and they typically have a much longer lifespan than the larger ones. Our sun is a medium-sized star, so it's not a dwarf, and I think it has what, billions of years to live. Someone can look it up. Anyway, I am definitely sidetracking. Alrighty, so nothing else that I need to go through here. I'm gonna go grab something to eat, and then I'll be back to answer questions. And Mark is typing something. I'm gonna wait a little bit. You guys can sign up if you want to. About 5 billion years more, we are halfway through its lifespan. Oh, okay, cool. And I think with our sun, it does expand as it gets old. And I think that expansion is going to push the photosphere past the orbit of Earth. So Earth is going to be toast, literally, when that happens. Fortunately, I won't live long enough to see that happen. Thank you, Mark, for that little tidbit. Alright, so I'm going to sign off from the live feed in Discord, and then I'll also stop the streaming. Alright.